We can now continue to our local experts, as we call them, with Guy Austern. Guy Austern is an assistant professor, he's a researcher, architect, computational designer, software developer. He is the head of the computational design and machine learning lab at the Technion, which focuses on using deep learning to solve architecture problems in design, analysis, and fabrication. The floor is yours.
Thank you. Wow, it's a bit hard speaking at the so and and especially since this lecture is going to be a bit strange for me. I was thinking what to say for this conference, and I wanted to say something that I don't want to say. What would it mean? I want to say something that's different. I didn't want to show all my students' work, especially since they're going to present their work in the next session. So, history session instead, and it's a very personal history session. I'm not a historian. I am an avid computational designer, and I like computational history, and it's kind of my take on it. It's a very personal take. Yeah. Also, which like you also have a computer science background. So anyway, yeah, this is AutoCAD, 1987. Just saw this like the other day. He's happy, right? But he's doing the same stuff architects have always been doing. But we'll get there in a second. So cities are an old thing, and they grew from the environmental necessity of just putting a lot of people in the same place at the same time. And quite a long time ago, we kind of found that we need to design that. We need to give rules and order to these things. And the Romans, like everything, they had a theory of urban design. They talked about the autonomous streets and the forum and the main streets. And they also had tools. Now, their tools were very primitive. They had pens, and it wasn't even paper, it was papyrus, and some sort of rulers. But that was enough for urban design at that time. And I think it's these two things, the theory and the tools, that I'm going to try to make sense of in this lecture. It's a bit ambitious. This goes on, right? So fast forward almost 2,000 years, and tools have not changed much. The pens have improved a bit. And urban design is still more or less the same tools. Theories have changed. Like we see Stradine introducing the diagonal. We see the garden city, and Ebenezer Howard with his three magnets, and then how this becomes implemented as a city, and then the suburbs that come out of it, which I don't even want to talk about. But so we have different theories all the time, but the tools remain more or less the same, right? This is being Israel. This is like maybe the most brave theory and the most horrible consequence, which you see now everywhere in the world. But it's all drawn on these pens and paper, on pieces of paper, and then something happens. 1948, ENIAC. This is not actually the first computer; it's more like the second one. And suddenly, we're able to process a lot of numbers, bits actually, not even numbers, at the same time, and things start to change. Very quickly, architects understand that they want to use this for urban design. So they have this idea that, okay, we have computers, we want to design stuff with them. Computers at that time, in the 70s, are not really strong. They're very, very big, very hard to get your hands on one. And they try to make cities grow. They just put a lot of blocks, and they say, oh, well, this looks like an old settlement, right, with vernacular, and everybody's kind of like, okay, what can we do with this? And it more or less stops. And then some theory comes along. So Bill Hillier, and so this is not a computer generated diagram. This is a hand-drawn diagram because his theory is before this could have been implemented with a computer. But it makes sense of space. It's like a computational theory of how cities should look like, how they behave. Actually, it's more about looking at the cities and how they should be. And over time, in 20, 30, I remember this is already 2008, and I was working with Axel, this very old space syntax application, 1,000 probably, and you could only do like a really small patch and it will take you one day. But over time, like we had first a theory, and the computation kind of caught up to it, and now space syntax is this big thing that everybody's using it. We've heard today, like an axial map, this is an axial map. And this goes on, of course, in Michael Batty. And he starts to talk about how cities grow. And he's learning from computational concepts, stellar automata, basically. And they're applied to urban fabrics. This is kind of where I start to join the story. This starts to be my personal perspective. I read this book in 2006 when it came out, and then I was doing a studio with Yasha. And I said, okay, I have to program a city that grows. And it was difficult at the time. There were computers already. This is not olden times, but I had to write everything myself in a Visual Studio script and run it in 3D Max. But basically, the idea of a city that grows was very prominent there. And it was well accepted when I presented it here, almost 20 years ago. But then some people, I remember some people got so upset. They're like, you want to take our jobs, and it doesn't make sense. And also your city sucks. Like, this is not a real city. It's just a bunch of blocks. Actually, the model was built from Lego. And that's an indication that your project is wrong, right? If you can build it from Lego, but that it's cool. And then something happens. 2007, in Holland, this guy invents a very different way to write code. And the world changes very, very quickly. Suddenly, architects can code. And from 2007, when I submitted my final project, I think 3-4 years later, everybody now can do Grasshopper. Everybody here, I don't even need to introduce Grasshopper anymore, I hope. Right? Okay. And this very quickly, now a tool has changed, right? So this is not a theory, this is a tool. But its implication, at least in the academia, this is not really, I don't know how much this went to practice, are huge, because now you can script a city. Now you can write a bunch of rules very quickly, or a few days. This is like a project I did for my master's, that you have like urban pathway and neighborhoods and secondary pathways, and then there's a section generator that comes through it and cuts out 3D massing, and you have something that looks at least like a city. I'm not sure it's a good city. It probably isn't. It's very difficult to test it, but it's easy. It's easy now to write code that generates cities. And this is like basically what's been happening for the last 10 years, more or less. You have, and I just give a few examples here. There are a lot more. Enriqueta Labares, who for these 10-15 years has been trying to see how networks grow, urban networks, and how you can design them according to their environment. And you have, of course, a parametricist approach, in which everything has to be really, really curvy. But yeah. And then you have people taking biological theories, like an anthill and how, and maybe we can build our cities like termites. Build our cities. These are all academic works, and each one of them has a different theory, but they're all sitting on the same basis on the Galapagos, the grasshopper that just came, and I just made the spoiler to myself, because I think maybe this is the most prominent, in my opinion, influence on this computational age. It's evolution and genetics, right? And so I don't need to introduce grasshopper, probably not also Galapagos. This idea that you can generate shapes, test them for some fitness criteria, and this is where sustainable design comes in, right? And this is kind of where the story goes, and then start using it to improve your design is something we couldn't do so long ago, and now we can. Yeah, I had to try it for myself, right? Right, and this is already quite old now, but the idea of a mechanism that generating examples and testing them for various fitness criteria and different scales and validating them. And then kind of going down in scales and trying to break things up. So this is a very nice movie. I think it took maybe 2 or 3 weeks to run this simulation because cities are big and it's a lot of data to process. And processing takes time, especially if you want to go to something that's a bit more, that's not as trivial as sun. You want to put wind or energy, then you have a problem. But this is something that kind of the world has been trying to work on. And you could see it still today in, like, I think, Jonathan so stuff like that. This is Anat. I had to put this slide because I saw you here. Her master project is also talking about how to use
Anat and Daphne.
Anat and Daphne, of course. Everything is, I hope, written up. So, and I think this very strong theoretical foundation of urban computational design today. And it's a very good one. And now we have something different, which is machine learning. And it's the new obsession. Everybody wants to have a piece of it. But it's a technological, it's not a theoretical development. And it's not very, very clear what, this is also why I asked you, is what we should do with it, right? So in the last 2, 3, 5 years, there's been a lot of research about urban machine learning. This is from my doctorate student, Dr. Susan Corral, who will be presenting the rest of her work later. But she really tried, and we have now urban ML work doing in a lot of fields, and environment here is maybe the focus of this conference, but it goes a lot of ways. I think one of the things we see, it's not going in one way. It's going in many, many, many different ways. I won't get into this. It's also what you talked about, surrogate modeling and about speed in machine learning. So this is very, very apparent, especially in the urban scale. Simulations that took a long, long time, not so long ago, we can now maybe teach the machine to learn, because machine learning, you spend a lot of time training the models, but then they run really, really quickly. So we see examples, 2 examples of that in Corral's work, and Corral and Professor Roman, and the work of Yosifov and Daphne Fischer-Wirtzman, which you'll see. So I will not talk about, but they talk about this speed. They're based about the fact that if you can use machine learning to automate the process that was time consuming, suddenly you can scale it up. You can apply it to whole cities, maybe even whole countries, which you just couldn't before. I'm running out of time. Yeah, just some thoughts, right? So fast inference, I just kind of described slow learning. machine learning, unlike heuristics, can learn from data sets, from examples. You don't have to be explicit, but then you need huge data set. And I know you said data is available, but it's not easy finding the data. And even if you have the data, tagging the data is killing all of us, right? Half of our work is just kind of writing what is what. It can perform tasks that previously humans or very strong computers can do, but it kind of tends to overfit. You feed it with data, so it learns to do something on that data. And if you try to do something on something else, which a human could do, and sometimes a heuristic model, like a simulation, could do, so the machine learning model is not necessarily well adapted to that. And of course, that there is the potential versus hype. This is probably the wrong way to go. Yeah, I can ask GPT to generate a futuristic city. This is not urbanism. This is science. This is not even science fiction. It's just a pretty image. So this is not the direction, although people kind of expect it to be. Yeah, I land on the question. I just don't know. So thank you.